Alright, so we're going to keep going. We're in chapter 9. We're talking about synthesis of ethers. Number 7. And we talked about, we showed an SN2 manner to do this. Let's talk about another SN2 synthesis of ethers to make cyclic ethers. Cyclic ethers. So this is pretty easy. We're basically going to do that same thing we just did, the Williamson ether synthesis, but to make something like THF, tetrahydrofuran, the cyclic 5-member ring ether. 1, 2, 3. We have 4 carbons, right? Okay, so what do you think happens here? We have H-, just like we talked about before. NaH is a strong basic hydride, and so yeah, we just circle lone pair, grab the proton, and there we go. That makes the alkoxide, just like any other Williamson style problem, and then the tax kicks it off, kicks off the BR, and that creates the cyclic ether. Okay. Alright, so that's an example of making a cyclic ether. We can do this to make epoxides. Remember epoxides? Epoxides from the PowerPoint is like a cyclic 3-member ring ether. You can also do the same thing to make an epoxide. So how does that work? Same exact way. Grab the proton, make the alkoxide, and then we'll just sort of sneak in there and do that. Kicks off the BR and you make the epoxide. Okay? So normal SN2 are, the normal types of SN2 reactions we've seen are all called intermolecular SN2. These are SN2 that are within the same molecule, so these are both called not intermolecular, but these are called intramolecular. Intramolecular SN2 versus intermolecular, which is between 2 different molecules. Okay. Intramolecular. These are both examples of intramolecular SN2 reactions, alright? Okay. And these are both, these are SN2 style. What about making ether via alcohol and sulfuric acid? This is a different style of reaction. It's another way to, rather than using base, what about the use of acid, H2SO4, H2SO4. So the book mentions this. I'm just going to briefly skim this, briefly mention. Just because this is a kind of industrial synthesis, and it is a widespread method for the synthesis of diethyl ether. H plus H2SO4. So for example, ethanol is produced in like ton scale by the reaction of ethanol. Ethanol is reacted with sulfuric acid in ton scale to make diethyl ether. Okay? So this is like kind of how most of the ether in the world is produced. It's not a general method, but it just works really well for simple molecules like this. So how does it work? It's an SN2 reaction. This is going to be an SN2 reaction, but we need a good leaving group and we need a nucleophile, right? So what happens is first one of these reacts with H+, and protonates the oxygen and makes a good leaving group. And then another one reacts as a nucleophile. So we have this is going to be electrophile, this is going to be nucleophile. This one attacks, kicks off the other one as a leaving group, and you make the product. Okay? So this is just kind of another example of a SN2 style reaction. This is not a terribly good nucleophile, but this does work, and they're able to make like ton scale of diethyl ether. Okay, so that's using acid as a way to do this SN2 reaction. There's one more example. This is SN2. There's another way, another example doing this with SN1 chemistry. And a different example. So if I have ethanol and a tertiary alcohol, okay, tertiary alcohols open the door up to SN1 chemistry, right? Because of tertiary carbocations. This is a way to H+, which is H2SO4, to make ether be an SN1 style reaction. Alright, so what's the ether going to look like? You can imagine it's going to be 2 carbons connected to tert-butyl, and okay, so a tert-butyl ether, right? Here we did kind of SN2 style chemistry, using acid to make a good leaving group. And here we're actually doing SN1 style chemistry to make a tert-butyl ether. And how does this work? How does this work? What's the mechanism of this? Okay, so with a tertiary alcohol, you think about carbocations, right? And so what happens is we protonate this alcohol, when you make a good leaving group on a tertiary carbon, what happens? Make a good leaving group on a tertiary carbon, what happens? The leaving group goes away. And now we have a tertiary carbocation. Okay. And how do we connect that ethoxy group onto the tert-butyl? Now I'm just going to draw a big long arrow. Okay, so ethanol can attack that. Ah, now we're almost done here, right, with that. What's missing? If ethanol attacks, now you have a proton on the oxygen, and then just something takes it off, like maybe ethanol takes it off. It takes off the proton. And you just made a tert-butyl ether via SN1 chemistry. Okay. Okay, so we talked about 2 ways to make ethers. Either SN2 or SN1, right? And either using base or acid. So those are a couple ways to make ethers. Now let's talk about reactions of ethers. reactions of ethers. Okay. Alright, so reactions of ethers. Things that might degrade an ether or destroy it or cleave it or something like that. So generally speaking, ethers are very stable. Very stable. But the one thing that will react with ethers is acid. So ethers can degrade or react with acid. Can degrade, it depends on your definition of degrade, I guess. React with acid. Okay? Alright, so there's a couple ways to do this. There's 3 examples. I just go through these 3 different situations or examples. Book talks about a couple other ways. Best way to do these is just understand my three different situations. Acid cleavage of ethers. Three situations or examples. I'm never gonna, like on the exam and quizzes and things, I'm never going to extend out of these 3 different situations. Alright? Okay, so our first situation or example is going to be if you have a primary or a secondary, a primary / secondary ether reacting with a nucleophilic acid. Okay, so what I mean by this, I mean a primary on one side, a secondary on the other, and I react with a nucleophilic acid. What's a nucleophilic acid? What kind of, maybe it's an acid with a nucleophilic conjugate base, like HBr or something like that. HBr, etc. Nucleophilic acid. This is going to be an SN2 cleavage. SN2. Okay. So it's going to be an SN2 style cleavage reaction. Let's just show an example of this. Isopropyl on one side, ethyl on the other. React with HBr. Okay. And I'm not going to just give away the product, I'm going to have us step through it. So what do you think is going to happen? It's a cleavage reaction, there's acid, there's Br. I say SN2, but the first thing that happens is protonation of the oxygen. Okay? So the oxygen is going to act as a base, grab the proton, and now I draw the proton on the top. It'll help us when we're thinking about this. Okay, so we have the protonated ether, and we have Br minus, right? Okay, and the Br minus is deciding which side to attack. Are we going to attack the left side or are we going to attack the right side? You make the decision. Okay, it's SN2. SN2, does that care about steric hindrance? Yes or no? The answer is yes, of course. SN2 does not like sterically hindered environments, right? So if you're the Br minus and you're going to undergo an SN2 reaction, you're going to attack the right side here. And what are the products? Isopropyl alcohol and ethyl bromide, bromoethane. Okay, that's our first situation. Like a primary, secondary ether with a nucleophilic acid. If you did a primary and a primary / primary ether, like diethyl ether, it would do the same thing. But I'm trying to show an environment where we have difference. We have a secondary on one side, primary on the other. The nucleophile attacks the primary side. Okay? Next, we have 3 different situations. I try to simplify these and just, we're always going to be within these 3 situations. If we have a tertiary ether on either side, tertiary ether with nucleophilic acid, a tertiary ether with a nucleophilic acid, this can be SN1, not SN2. And by SN1 it implies what? What intermediate do we have with SN1 reactions? Carbocation, right? So let's show, now it doesn't really matter, as long as one side's tertiary this happens. So I'm going to do a secondary slash tertiary, for example. And HBr, okay, and so the nucleophile here in the top and wound up on the less substituted side when it cleaved. Here the nucleophile is going to wind up on the more substituted side, and it's going to be through an SN1 style reaction. Weird. Not that weird, but a little weird. See the difference? Less substituted side, more substituted side. So what's the mechanism? Now I'm going to do the same thing. Protonate the oxygen. Okay. On a tertiary substituted molecule with a good leaving group, because now that thing's a good leaving group, what happens? Whenever you have a tertiary carbon with a good leaving group, you make carbocation. Ah, okay, so now that made that, and then we also have a carbocation. What's the carbocation going to do to that? What's Br minus going to do to the carbocation? It's going to react with it. Ah, so that was the SN1 cleavage of an ether. SN1 cleavage of an ether, but you need a tertiary substituted ether for this to happen, and you get SN1 cleavage. Okay. Okay. Third example. One of the sides is a tertiary ether, but rather than a nucleophilic acid, we're going to use a non-nuc acid. Non-nucleophilic acid. What were the non-nucleophilic acids that we learned about? We learned they were this chapter, H2SO4 or H3PO4. Sulfuric acid or phosphoric acid are non-nucleophilic acids. Okay. And if nucleophilic acids cause SN1, what do non-nucleophilic acids cause? Not S anything. E1. So this is going to be an E1 reaction, and this is via carbocation. So this will actually cause a carbocation formation. And what's the product of an E1 reaction? Elimination. You make alkenes, right? So let's do the same exact substrate, secondary or tertiary, and we'll do a non-nucleophilic acid like H2SO4. Sometimes a little bit of heat is applied, a little bit of temperature. And here we cleave and we make the tertiary side gets converted to an alkene. So it's isobutylene, it's just a 4-carbon alkene. What's the mechanism of this reaction? Just like we did before, first step is always protonation with our super duper acid. So HSO4 minus whatever is formed. Okay, I'm going to put a square around the products and let's figure out the mechanism. So we protonate. What do you always do if you have a good leaving group on a tertiary carbon? Just like we did above. Good leaving group on a tertiary carbon, good leaving group on a tertiary carbon, you make a carbocation. Ah, there we go. Makes our product isopropyl alcohol, just like this made our product isopropyl alcohol. And we make a carbocation. Okay? And how do we finish this up and make the alkene with a non-nucleophilic acid? So it's not going to be a nucleophile, like it doesn't have like Br minus or something. How do we make the alkene? How do we finish up this E1 reaction, like water or some mild base that's around, takes the proton, and that's the E1 style reaction that creates the alkene, just like we learned about in chapter 7. Okay? So what we just saw is kind of cool. We're still on number 8, which is reactions of ethers. And of course, number 7 was a synthesis of ethers. So we have ways to make ethers, we have ways to degrade ethers, right? So what this allows, and I'm going to say this is cool, is the tert-butyl ether. Tert-butyl ether is, right, that's what I mean by tert-butyl ether, is that. Is useful to temporarily mask an alcohol. We'll see what I mean by that and why that's cool in a second. The idea is, like, what if I have a molecule that looks like this? I have R1OH. I have an alcohol, but R1 is something else in the molecule, and I want to do something to that R1. I want to change it. But the alcohol might have some problems because alcohols have their own reactivity. I can actually kind of block that alcohol and make a tert-butyl ether. How do we do that? We just learned how to do that, right? It was a section 7, 2 sections ago. We were like, oh, how do we take a primary alcohol or secondary alcohol or whatever and attach a tert-butyl ether? Remember how we did that? We used tert-butyl alcohol and a little bit of H plus, right? H plus meaning like H2SO4 or something. A little bit of acid. How did that work? Of course, the alcohol got protonated and fell off, made a carbocation, right? Made a tertiary carbocation. And then this alcohol attacked and then lost its proton, and then we made a tert-butyl ether. So what if now we want to take R1 and do some stuff? We're like, all right, arrow, arrow, arrow. We're going to say, now we're going to make R2. Like we change whatever the R group is. And we'll do that in a second. And then we're like, okay, now we have this tert-butyl ether, we want to get rid of it. How do we do that? We just learned how to do that also. We just learned how to take it off, maybe with acid, like H2SO4. I might just say H3O+, like a strong acid, strong non-nucleophilic acid, and that would create what? As we just learned in the previous, in 8, just a second ago. We learned that this would cleave the ether in a, what kind of style? SN1 or E1? This is E1. E1 cleavage. Ether cleavage. And return us back to the alcohol world. We went from alcohol to ether, did a couple steps to maybe change the other side of the molecule, and then we cleaved the ether and we made that. Now this is cool. This is a nice impurity because it's a gas. It's isobutylene gas. It just bubbles away. It's a gas, right? So of all kind of impurities or byproducts, that's actually kind of a good one because it just goes away. Okay. And I'm going to go a step further and say this tert-butyl ether, I'm going to give it a name. I'm going to say it's a masked alcohol. A masked alcohol, because it's kind of like it's like a temporary state of an alcohol, right? we want to maybe block this alcohol, have it be something else, and so we can, and the reason for that is because alcohols sometimes cause problems. They have their own weird reactivity, and they could be an acid, for example. So when we block the alcohol, it might be an ether, and I call it a masked alcohol. This is a masked alcohol. This tert-butyl ether is a masked alcohol. Another name for it I like to use is it's an alcohol in disguise. It's an alcohol in disguise. It's an alcohol in disguise because it's like we just had Halloween. This is the Halloween costume of an alcohol, right? Because it can return back to its normal alcohol state just by using sulfuric acid. Alcohol in disguise. Okay, so, and I'm also going to call it one more thing. The more chemistry appropriate name for this idea is a protecting group. Protecting group. So what is a protecting group? A protecting group. This is an example of a protecting group, and we'll show why it's appropriate and why it's kind of cool next. Okay, protecting group. Protecting groups. What's a protecting group? This is topic number 9, that's what it is. Or PG. PG is this concept that we're going to describe, protecting group. So, we're going to say that sometimes a functional group, FG, can cause problems. If you're doing a multi-step synthesis, sometimes a functional group is like problematic, and so therefore we sometimes will temporarily mask it as another functional group. That's the concept that we're describing. Sometimes like an alcohol might be a problem, so let's make it an ether temporarily. We'll turn an alcohol into an ether, and then now it's an ether, and then we can take the ether off later and return it back to an alcohol. That's the whole concept of protecting groups. So I'll define it. Protection. Definition. Temporarily mask one functional group as another to limit its reactivity. Temporarily mask one functional group as another, or disguise it, or whatever you want to call it, to limit its reactivity. So here is an example of first we're going to show kind of a failed synthesis, and then we're going to fix it. Alright, we have 3 carbons, hydroxy, 3 carbons, bromide, and we might ask, question mark, how could we convert this into this secondary alcohol? How could we convert that into a secondary alcohol like that? I mean, it looks like, kind of like, if you think about Grignard, for example, because we know that like we can convert a bromide to an alcohol using Grignard. It almost looks like, well, we have 3 carbons there, and we want to add almost like this whole, there's the 3 carbons on the product, right? There's the 3 carbons. We want to add this whole thing, right? So it's like 3 plus X makes what? 1, 2, 3, 4, and then 6 on there. 3 10, right? 3 plus X is 10, so X is 7, right? So it must be a 7 carbon piece, and the 7 carbon piece, and also remember with the Grignards that Grignards and organolithiums, what do they react with? If I can make this into a Grignard, for example, what are the substrate of a Grignard? It attacks a something or a something, and it makes a alcohol, right? What are the things they react with? Ketones and aldehydes, right? And I also see that being a secondary alcohol, does that mean we're going to attack a ketone or aldehyde, or like formaldehyde? So this is where if you look back in chapter 8, we talked about this. For like, you know, if we want to make a secondary alcohol, you always react with an aldehyde. So what is the aldehyde going to look like? It's going to look like, this is going to be the aldehyde, right? It's that with an aldehyde, right? A C double bond O version of that. So the aldehyde version of that. It's benzene, C double bond O. It's called benzaldehyde, right? Okay, so this should be a simple problem, right? But it's not, and we'll see what the problem is. Alright, so it's simple. We just make a Grignard. Mg makes a Grignard, right? Alright, we got a Grignard. Yay! Now all we have to do is react the Grignard with the 7 carbon benzaldehyde, right? What's that, right? Benzaldehyde is the benzene with the aldehyde, and should just make that nucleophile attack and kick electrons up onto oxygen. But that does not work. And the reason, I mean, it looks beautiful, right? It does not happen this way. And the reason is because, oh no, the alcohol. Remember that Grignards have 2 reactivities. Yes, they love to attack as a nucleophile, attack an electrophile, right? It loves to attack electrophiles, but they're also super basic. And the pKa of this alcohol is what? It's like 15. That's fairly acidic, and a Grignard is, rather than be a nucleophile, like we want it to be a nucleophile, it's just going to be a base. So it's just going to destroy itself and rip off that proton and make what? It's just going to turn CH2 into CH3, right? It's going to make an alkane, and it's going to make O minus CH3. Oh no, it just destroyed itself. Now the Grignard's gone, right? And we have mGBr plus. You basically defeated the whole thing you were trying to do. You're trying to do a Grignard, but you ended up just destroying the Grignard. Okay. And so what's the solution going to be? Just mask the alcohol as an ether. And we'll just use a terbutyl ether because we know how to put it on and take it off really easily. And then it solves all this problem. Okay, so that's the protecting group strategy in a summary. Sometimes a functional group can cause problems, so therefore we temporarily mask it as another functional group. We define protection as temporarily mask one functional group as another to limit its reactivity. So let's do that now. Okay, solution. So we're going to do the same exact thing. And our goal is the same. Right? And what's the bond we're making? This is the bond. That's the bond we're creating. Okay? And so cool. There's the bond we're going to make. So how are we going to do this? All we have to do is, very first step will be make the terbutyl ether. The very last step will be remove the terbutyl ether. So, and then we just do the Grignard just like normal. Okay, so how do we make that terbutyl ether? tert-butyl alcohol and H+. H+ would mean sulfuric acid, but if we just say H+, that's understood as a strong acid here. Okay. Cool. Oh, we made a tert-butyl ether. Now we do what? Now we're ready to make our Grignard. And now the Grignard is totally happy because there's no alcohol around. So we just throw in the Mg. And that creates the Grignard. Alright. Now we're ready to do our Grignard reaction. What's the substrate we're using? The thing we're attacking? Of course, I use my thumb usually. If I have a squiggly line, I can say, well, that's going to be kind of the Grignard piece, of course, with the alcohol protected. And the thing we're attacking, the electrophile, is that. But of course, we don't attack alcohols. We attack an aldehyde, for example, to make the alcohol. So what is it? It's 7 carbons. It's benzaldehyde. Benzene, aldehyde here. Cool, there's our aldehyde. And what's our second step of Grignard is always like water, H2O. And I can draw the mechanism of this. It's really easy. I just circle the bond, attack, electrons go up. Okay, so cool. We just made the cool secondary alcohol that we want. But we still have the sorry, it's a little drawn. There's the benzene. Okay. I just flipped it over, right? So the Grignard attacks the benzaldehyde. That makes the secondary alcohol. I've just flipped it over. And then last step is how do we take off the tert-butyl ether? As we learned, we know how to put it on. We know how to take it off. So it's H3O plus, or like sulfuric acid, H2SO4. Maybe a little bit of heat. That just means heat, and it just plops off. What is our byproduct of that? Isobutylene, which is the gas, right? So this whole thing falls off as isobutylene, which is the gas. Okay, and then we get this product. So that's the overall synthesis. All we have to do is install the tert-butyl ether, do the Grignard, take off the tert-butyl ether, and we're done. Okay. Okay, you should practice. I'm not going to do it. The mechanism of formation and the mechanism of removal. How do you put on the tert-butyl ether? Like practice that, see if you can do that mechanism, right? And then you can do the mechanism of removal. Okay. So and I'm just going to abbreviate these. I'm not going to draw them out. I'm going to say, in this case, I'm just going to say alcohol, or there we go, alcohol. R just means random piece of the molecule. That would be like an abbreviated, mechanism. That's like an abbreviated form of the structure that shows how does the primary alcohol get converted to tert-butyl ether. We just showed you, so you just saw it like a couple minutes ago. And then the mechanism of removal. So try these and see if you can do them. If not, you can come to office hours. Good mechanism practice, right? See if you can do these mechanisms. Cool. All right. All right, we have one more topic in Chapter 9. Epoxides, like we were talking about before. Epoxides. This is a pretty important thing in terms of seeing it through the end of Organic 2. We saw that we introduced the concept in the PowerPoint, and they also have another name called oxycyclopropane. Oxycyclopropane, which is not very commonly used, but generally speaking, though, it's a cyclic ether with three-member ring ether. A very common reaction is that nucleophiles can just attack them. Most ethers you can't do this because most ethers are stable. But why do you think oxygen with a three-member ring is going to be maybe less stable and like open up like this? Why do you think? And H2O. Why do you think that might happen? We always have a second step of water or something, and then you get... Why do you think a epoxide might be reactive, like just opening up like this? The reason is it's tiny, it's ring-strained, right? Just like a cyclopropane is kind of ring-strained. Alright, so first we got to explain how to make them, making epoxides, and then we're going to show a couple reactions of them. I'm actually jumping ahead a couple chapters to show this way, just because it's really the way that everybody uses. There's a couple ways to make epoxides, but this stuff called mCPBA is it's the easiest way, I think, to make epoxides. It's got a cool mechanism. What is mCPBA? mCPBA is this molecule. It is chlorine. It's a benzene with a C double bond O, and then this is kind of a weird functional group you've never seen before. It's kind of like a carboxylic acid, but this is an extra oxygen. It's called a peroxycarboxylic acid. Peroxycarboxylic acid. So mCPBA stands for, the name stands for meta chloro peroxybenzoic acid. Metachloroperoxybenzoic acid. That's metachloroperoxybenzoic acid, mCPBA. Not much to really talk about it as a name, but just a little bit on benzenes. So this benzene has the chlorine and this thing in this relationship. I'm just going to mention something about that. So in the benzene chapter, which is actually Organic 2, we talk about these different kinds of benzenes where you have like X and Y, X and Y. And like if you have two different things on a benzene, they have names like X and Y, X and Y, X and Y. You'll see this in Organic 2, but this is called ortho. This is called meta. This is called para. Okay, ortho, meta, and para is just this relationship of next door, separated by 1, separated by 2. And that's where the meta comes from. Metachloroperoxybenzoic acid. Alright. Anyway, there's not much else to talk about it with the name. But what's the actual reaction? Because the reaction's cool. It takes an alkene. It takes an alkene and it makes an epoxide in a very simple, elegant manner. And we use mCPBA. mCPBA is the reagent, so mCPBA. mCPBA is a reagent that converts an alkene to an epoxide through a really cool mechanism. So let's show the mechanism a bit. So to show the mechanism is redraw the alkene, and I'm going to draw mCPBA. I'm going to redraw it, but I'm going to abbreviate it a little bit. I'm going to have a little oxygen and a hydrogen, other oxygen, C double bond O, AR. What was AR? AR is the benzene with the chlorine, but that's irrelevant. We don't really care about that. The big thing though is drawing the alkene and this oxygen and the hydrogen and this whole thing kind of arranged like this, and then a dot 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 dot. Okay? Alright, so there we go. And there's the epoxide. And now the really fun mechanism occurs. Alright, so what happens? This is a concerted mechanism, so a bunch of stuff's all going to happen simultaneously. Concerted. Remember concerted? It's like SN2 is concerted, right? Where the nucleophile attacks and the leaving group goes away all at the same time. And I'm going to draw one more arrow, or dot dot dot. Dot 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 dot. Alright. So everything happens simultaneously, and I always start this, just because the way I learned it, from the double bond O. The double bond O is going to grab the proton. As we know, protons like to be grabbed by other atoms, so the double bond O is going to grab the proton. And then what's going to happen? Well, we got to keep moving the electrons around, so if the double bond O grabs the proton, well then this goes there. That bond goes to the carbon, pair of electrons. The double bond goes there. I just swung it around that way, or you could go through the ring, but whatever. The point is that the pair of electrons form a bond to the oxygen, and this goes there. And that actually creates a new double bond O. Alright? So throughout this process, what happens? You make the epoxide. That's it. Pretty cool little mechanism. mCPBA is just a reagent that creates alkene, converts an alkene to an epoxide. What's the byproduct? Well, what do you think it is? Let's follow through with the arrows, right? We made the epoxide, and then it's like, now we make a double bond O there, and a single bond O there, and a single bond to H. So it just makes that as a byproduct. And what is that functional group? It's a carboxylic acid. So the net reaction converts a peroxybenzoic acid, which is this weird OOH carboxylic acid, to a normal carboxylic acid. Okay, so now we know how to make them. That's all you do to make them. It's really easy. This is all. The book does not present this in Chapter 9. I think they move it to Chapter 12. We'll get to Chapter 12 shortly. So you'll see this later in Chapter 12, 12:10 actually. But now we know it, and I like this method as the primary way to make epoxides. Everybody in the universe that makes epoxides does it this way. mCPBA is a wonderful reagent. All right. Okay, so now that we know how to make it, now we have to talk about opening. So, opening epoxides. And just like when we talked about ethers and ether cleavage, there's like only a couple ways that we talk about to open epoxides, but you need to know all three of them. So I'll list them and then I'll talk about them. First one, number one, is non-acidic nucleophile. Non-acidic nucleophile, and this will always be an SN2 style reaction. If you're making index cards, this might, when we fill this all out, this might be a good index card, as well as the whole ether cleavage concept, because we did that, and that was like 3 different examples of ether cleavage. This is a little analogous to that. Okay, if we have acidic nucleophile, it's either going to be SN2 or SN1. depending on the epoxide. Okay? Acidic nucleophile. So if it's non-acidic, it's always SN2. If it's an acidic nucleophile, it can be SN2 or it can be SN1. I'll give you a hint. When does SN1 always seem to happen? Is it primary, secondary, tertiary? It's always going to be on tertiary. So it'll be some epoxides that look like this, which has like a tertiary carbon. These are going to be, with acidic nucleophiles, are going to be SN1 style. All right. Okay, so we're still on epoxides. I think this is the last topic of this chapter. So, epoxides. Opening them. Opening epoxides. And we talked about the three kinds. This is the first one. This is SN2-like. And this is with non-acidic nucleophiles. If it's a non-acidic nucleophile, it always and only does SN2-like opening. This includes Grignards. So Grignards are non-acidic, right? They're extremely basic. All right, so I'm going to just show some examples. Whoops. Alright, so here we go. H2O, number 1. Na plus, S minus. Okay, so this is, you know, if you look at the nucleophile, Na plus, S minus, maybe throw some DMF in. This is just looks like a normal old SN2 reaction, right? And it opens up exactly like an SN2. You don't need water as a second step, but what's the mechanism, and then we'll draw the product. So SN2 opening will always be from the least hindered side of the epoxide. Least hindered side. Okay, so what's the least hindered side? Is it the left or the right? Well, the right side is least hindered. It just opens it up. What's the product? What's the intermediate? There's the O minus. I just flipped it down. And now that thing, the sulfur, is attached here. Cool. Alright. And where's the bond we made? I sometimes draw the bond we made with a little squiggly line. It's like, yeah, we made that bond. Noticing that the nucleophile, which is this whole sulfur thing, is connected to one bond over from where the oxygen is. Okay? Because when you... Okay, yeah. That's going to be a big deal. We're going to see that in a second again. And what does water do? O minus is a proton donor. There we go. We could either do the zigzaggy way, or you know, this might be better to draw like up, down, up, rather than down, up, down. So that I like this zigzag a little better. But yeah, that's the product. It's an SN2 opening of the epoxide. Okay? SN2 like opening of the epoxide. Okay, let's do another one. Just kind of using the old SN2 style. Nucleophiles that you know of from before. So these are all going to be non-acidic. Non-acidic is always going to be SN2-like. Okay. Na plus Cn minus. Non-acidic, right? There's no acid. It's not like HBr or something like that. So it's going to be SN2-like, and even though this is tertiary, that's all irrelevant. Non-acidic will always be SN2-like. So, being SN2-like, is it going to tackle the left or the right? It's going to tackle the right. That's the product. What's the mechanism? What's the mechanism? So, attacks. And then we just give a proton with water. So O- grabs a proton from water. Okay? Alright. What's the product of all of these openings? They're always alcohols, right? So the epoxide gets opened up to make alcohols. So we call this opening regioselective. Opening is called regioselective. And the regioselective, all that means is that it's attacking like the least hindered side. It's specific to a region of the molecule. Regioselective means attacking like the least hindered side. Alright, so just one more example. Let's draw random epoxide, and if I'm like thinking, oh, I'm the nucleophile, am I going to attack the left or the right in this sort of SN2 style approach? Yeah, it's always going to attack the right, and that's due to it's like less hindered, right, on the right side. Okay. And if we grab a proton, second step's always like water to protonate the oxygen. And there we go. Another example. So, epoxide. We're in the opening section. Opening of epoxides. mCPBA. Let's draw Na plus, S minus. Okay, so what's going on here? Step 1 makes the epoxide, right? That's what we know. mCPBA makes epoxides, and then this thing is going to attack the epoxide, and then we're going to protonate the oxygen. So I'm going to abbreviate the benzene as pH. There's the epoxide. mCPBA makes the epoxide. Open it up on the least hindered side. Right? One carbon, 1, 2, 3 carbons. There's my 3 carbons, and then the sulfur has 2, so we attach 2. And then what does water do? It gives a proton to oxygen. The final product is that. Okay. Okay, so more examples of the SN2 style, right? We're on the SN2 style, which is non-acidic, because acidic is going to be totally different. So we're cool with these non-acidic openings so far. is always SN2 style, which always means least hindered side. Okay, so let's consider lithium aluminum hydride and Grignard type openings. Grignard organometallic. Because these are all also going to be in this sort of SN2 style category. Alright, so lithium aluminum hydride. Let's try random epoxide. And let's do lithium aluminum hydride H2O. Okay, so I'll just draw the product and then draw the mechanism. So we know that lithium aluminum hydride is a nucleophilic hydride, right? It's a nucleophilic H-, right? So it's just H- attacks, and it's going to attack the left side or the right side. It's going to attack the right side because that's the least hindered side. The product is that. How does it work? H-, I just put it in quotes because that's how we do this. I like to say we have this thing is equal to H dot minus, and it just attacks, right? Circle it, attack. Okay, so now we have our CH3, because it was CH2, now it's CH3. Water. Okay, what about another one? Let's do take this alkene, mCPBA. What does that make? It makes the epoxide. Let's throw in propyl Grignard. Propyl Grignard, MGBR, right? Propyl Grignard H2O. Alright, so propyl Grignard, it's just another nucleophile, right? Just like H- was nucleophile. It's another nucleophile. It's a 3-carbon nucleophile, right? Alright, so is it going to attack the top or the bottom? All these non-acidic nucleophiles will attack SN2 style, which would be the bottom in this case, the least hindered site. Circle the nucleophilic propyl group. Okay, so there's an intermediate. Propyl. Grab the proton from water, H2O, whatever. And what's the final product? So it's OH, right? Carbon, carbon, carbon. There's our final product. I'm going to point this out again in a second, but there's an interesting thing here, which, you know, that's especially for Grignards, because we know Grignards. Grignards attack ketones and aldehydes, right, so far, that you know of. Grignards attack ketones and aldehydes. And whenever they do that, they always, it's like the Grignard thing is always like adjacent to the OH. Like the OH is directly attached, right? But in epoxide, the Grignard thing is actually attached next door to where the alcohol is. We'll see that again, but just keep that in the back of your mind right now. Where the Grignard thing is, the thing that attacked, relative to where the OH is. Okay. We'll see that again in a second. Okay. Alright, so let's review a little bit on those Grignards and the kind of reactivity that we see. So if we have like bromide, I don't know. Yeah, we do magnesium, make a Grignard. Okay, we made a Grignard. And it's nucleophile, it loves to attack stuff. What are the things that we can attack? What did we learn before? I don't know, we'll show formaldehyde, right? And of course, when you attack formaldehyde with a Grignard, you make a primary alcohol. I'm not going to show all the arrows because, well, actually I can. Yeah, that's fine. Yeah, we learned this in chapter 8, right? So I can like circle it. Of course, it attacks the carbon and makes a primary alcohol. Where's the bond we just created? Squiggly line right there. There's our squiggly line of, you know, we make a bond between these two carbons, right? Carbon, carbon. All right. Okay. What about if we react with a 2-carbon epoxide? What's the product? Well, if this attacks there and opens up, attacks the carbon, opens up, carbon, carbon, what is 7 plus 2 is 9, so 6, 7, 8, 9. Okay, and I'm skipping the protonation because it's, of course, there's an intermediate. It attacks, then you have O minus. O minus grabs proton, but I'm skipping all that. Where's my squiggly line when I attack the epoxide? Oh, it's right there, right? Because that carbon attacked that carbon and it displaced the hydroxy group to the neighboring position. So I'm bringing up, is I just mentioned this a second ago, of like where the Grignard thing, you know, kind of what, like where it is in the product. Well, that was the Grignard thing, 7 carbons, and it's directly connected to OH. But in this case, when you attack an epoxide, it's like that was the Grignard thing, 7 carbons, and then the OH is on the neighboring carbon. So that's going to be a recurring theme, and we need to just get that straight in our mind. Where the OH is relative to where the squiggly line is, right? Where the OH is relative to where the squiggly line is. Okay? How about aldehyde? This is old stuff, right? Okay, so again, I can't draw arrows for every one of these, but of course that carbon attacks that. And you might remember from when we learned about this, opening an aldehyde always makes a secondary alcohol. And so the product, and you know, if you want to draw out all the mechanisms, you can do that. So there's the carbon. It gets a little congested here. CH2. Okay, let's do our math. 7 plus 1, 2, 3, 4, 5. 7 plus 5 should be 12, right? Let's see if we did it right. 6, 7, 8, 9, 10, 11, 12. Good. Where's my squiggly line? It's right there, right? There's my squiggly line. And again, like I said, when a Grignard attacks an aldehyde or a ketone, or formaldehyde, look at where the OH is relative to where the squiggly line is, right? Alright, water. Any more I should do? And also, what kind of alcohol? If you react with a aldehyde, you make a secondary alcohol. What kind of alcohol do you get if you react with formaldehyde? It's a primary alcohol. In this case, it depends on the epoxide. This happens to be a primary alcohol, but we have a couple general rules when we tech. Formaldehyde, normal aldehyde, or like a ketone. What do we get if we react with acetone, a ketone? And then you get a tertiary alcohol. All from chapter 8. And where is my squiggly line? Here. Well, it's right there. The squiggly line is between this carbon and where the ketone was, right? Okay, and look at where the squiggly line is relative to the OH. Alright. Okay, cool. And I'm just going to do one more. I'm just going to redraw my Grignard. And like this random epoxide. Of course. What's the product? I'll do mini mechanism. I'm not going to show the intermediate, but of course that carbon attacks, opens up, and you get attack from the least inner side. Where's my squiggly? Okay. Alright. I'm going to quickly there's two last things I wanted to mention, and it just goes together with all this, so I just want to get them out of the way. I may go over a minute or so. Okay, all of that was opening and non-acidic, right? They're all non-acidic nucleophiles. Grignards, all the other things. It's like some negatively charged nucleophile. So I just need to mention quickly opening epoxides, and we're going to we have SN2 that's acidic, and we're going to have SN1 that's acidic. I just got to mention these real quick. It's easy though. Acidic nucleophile. Okay. So this will be SN2 also, but it's going to be using an acidic nucleophile. So here's the example. HBr. Okay, now we have an acidic nucleophile. HBr is an acidic nucleophile. It's just going to be SN2. But we need to first protonate the oxygen. So with an acidic nucleophile, you protonate the oxygen. Okay, we protonate the oxygen. Alright, we protonated the oxygen, right? And now Br minus is deciding, where am I going to attack? Where am I going to attack in an SN2 style opening? Left or right? It's going to open onto the left. So what's our product? It just Br is attached, and we have how many carbons? 3 carbons. Cool. Okay. Alright, so that's the SN2 acidic opening, and I just got to show the SN1 acidic opening, and then we're done. Sorry if I'm over a minute or two, but now that'll be the the 3 realms of opening reactions. So let's do opening SN1 acidic, and then we'll be all done. There'll be a tiny bit more in this chapter, but we've done all the hard stuff. SN1 with acidic nucleophile. Alright, so this is last. We're going to do the same exact thing, but now if one of the sides is tertiary, then all it's going to do is reverse it, and it's going to be SN1. Okay, so the end product will be this. Okay, so not SN2 SN2 style, but SN1. It's really easy. Let's just do it real quick. Protonate. Okay. With a tertiary side, we'll do this SN1 style opening. I'm just going to draw my proton right there. Okay, we cool. And what happens if you have a good leaving group on a tertiary carbon? It opens up, and it actually opens like this. See how it opens? Okay, this is it. Alcohol. And how do we finish this up? Br minus does what? Attacks the tertiary. And we're done. Okay, so I will review this next time. I just wanted to mention it. Okay. The big thing is if you have an acidic nucleophile, this is the very end summary here. The big thing, if you have an acidic nucleophile like HBr, acidic nucleophile, if you have a tertiary, then it's going to be SN1, right? If you do not have a tertiary, like if you have a secondary or something like that, or any other kind of epoxide, anything but tertiary, it's always going to be SN2. Okay? So acidic nucleophile, if it's acidic nucleophile and you have a tertiary, it's going to be SN1. Anything else is going to be SN2, right, like this. All right, so I'll review that. And then anything that's non-acidic, including Grignards and all that, it's always going to be SN2 style, meaning it attacks the least inner side. Okay, cool. Sorry I went over a little bit, but that's the hard stuff in Chapter 9. We have a tiny bit more, and then we're onward to Chapter 11.